Okay, so in this lecture we are going to discuss the topics, that is double refraction, then geometry of the calcite crystal, Huygen's theory of double refraction, that is positive and negative crystals, then propagation of light in double refracting crystals, and the application of polarization, that is LCD. So let us discuss polarization by double refraction. This polarization by double refraction is also known commonly as birefringence for the phenomena that is known as double refraction. Then this phenomena of double refraction is shown by certain type of crystals such as calcite, quartz, tourmaline and so on in which when objects are seen through such type of crystals such as calcite, quartz and tourmaline, then instead of a single image you obtain two images of an object. So two images of an object are observed for certain orientations of these crystals, and this phenomena is called as the phenomena of double refraction or birefringence. Then you might be knowing about isotropic crystals and anisotropic crystals. What is mean by isotropic crystal? You know this, you have studied in 12th standard. What is mean by isotropic and anisotropic crystals? Hello?
Yes.
So what is mean by isotropic and what is mean by anisotropic?
Isotropic means molecules are arranged in same manner from all the direction.
Yes.
And anisotropic, they are arranged in different manner from different directions.
Yeah, means for isotropic crystals, the physical properties of the crystal are same in all the direction, while anisotropic crystals are those crystals in which physical properties of the crystal are different in different direction. So one of the physical property is refractive index mu, and for isotropic crystal this refractive index mu is same in all directions, while for anisotropic crystals this refractive index mu is different in different direction. Now here the crystals such as calcite, quartz, tourmaline and so on, Rochelli salt, these are the asymmetric crystals in which the physical properties of the crystal are different in different direction. Now we use generally this calcite crystal is used to study the phenomena of double refraction, and therefore it is important for us to know what is the geometry of this calcite crystal is. This calcite crystal is also commonly known as Iceland spar. It is also known as Iceland spar because of the fact that this crystal was found in Iceland, and therefore it is also known as Iceland spar. Earlier people were using this crystal for the amusement purposes because of the phenomena of double refraction. So instead of a single image of the object, two images of the objects are observed while observing the transmitted rays through this crystal. And therefore earlier this crystal was used for only the amusement purposes. Now this calcite is a crystal of calcium carbonate, so it is chemically CaCO3, that is calcium carbonate, and it occurs in nature in various forms. But if you break this crystal of calcite, then it always breaks in the form of a rhombohedron. So if you break that, it will again break in the form of a rhombohedron. If you still break it, it will always break in the form of a rhombohedron. Whatever be the small piece of the crystal is, it always take the shape of a rhombohedron. Then this rhombohedron, so this is the rhombohedron shape, and to this rhombohedron there are how many faces to this rhombohedron? This is one face which is A, B, C, D. This is another face which is H, C, D, E. one more face is EHGF, then the face is AFGB, then this is the face which is FEDA and GHCB. These are the faces. So how many faces are there to this rhombohedron?
6 faces.
6 faces.
6.
Now on there are 6 faces, and how many corners are there in this rhombohedron?
8 corners.
8 corners. Now out of these 8 corners of the rhombohedron, at all the 6 corners of the crystal, with this face, here you can see this angle with this face which is ABC. If you look at this face, then this angle is acute angle of 78 degree. Then with this face, say A, B and G, there is an acute angle of 78 degree, while with this face which is G, B and C, there is an obtuse angle of 102 degree. Is it clear?
Yes, sir.
And this is the case out for 6 corners out of 8 corners. So at this corner, this is the acute angle of 78 degree, this is also acute angle of 78 degree, and with this face, this total angle will be of 102 degree. So this is the case at all the remaining 6 corners, while at the 2 diametrically opposite corners, that is A and H of the crystal, here you can see that all the angles are obtuse angles of 102 degree. So all the angles are equal and they are obtuse angles of 102 degree, isn't it?
Yes, sir.
So at the 2 diametrically opposite corners of the crystal, or you may call them as diagonally opposite corners of the crystal, all the angles are obtuse angles and they are equal, while at the remaining 6 corners of the crystal, there are 2 acute angles of 78 degree and 1 obtuse angle of 102 degree. So the diametrically opposite corners at which all the angles are equal and obtuse angles of 102 degree, such corners, that is A and H of the crystal, such 2 corners, that is A and H of the crystal, they are known as blunt corners of the crystal. Such corners are known as blunt corners of the crystal. Then we define the optic axis of the crystal, and an optic axis is defined as an imaginary line drawn through the blunt corners of the crystal. So there is no such line which is physically present inside the crystal. It is just an imaginary line drawn through the crystal, or it is just a direction which is drawn through the crystal. Now what is the property of this optic axis is, though this is an asymmetric crystal, or though this is an anisotropic crystal for which physical properties are different in different direction, but along the direction of optic axis, if this is the direction of optic axis, then along the direction of optic axis, its physical properties will remain same. That is, one of the physical property is refractive index. So if you measure the refractive index at this point or this point or this point or this point, that is along the direction of optic axis, the value of refractive index mu will be same along the direction of optic axis. But for any other direction, if you measure the value of refractive index mu along this direction, if you measure the refractive index along this direction or along this direction or along this direction or along this direction of the crystal, then you will have different values of mu, that is refractive index, because the physical properties are different for physical properties of the crystal are different in different direction. But along the direction of optic axis, the value of refractive index mu remains unchanged. It means that physical properties of the crystal remains constant along the direction of optic axis of the crystal. Is it clear?
Yes, sir.
Okay. Then we define a plane called as a principal plane. See, this property is very important from MCQ type examination. Okay, physical properties of the crystal remains constant along the direction of optic axis. You should know about this property. Then we define principal plane for the calcite crystal, and principal plane is defined as a plane which is perpendicular to the two opposite faces of the crystal and which contains the direction of optic axis. So such a plane is defined as a principal plane. So if I draw a plane which contains the direction of optic axis and it is perpendicular to the two opposite faces of the crystal, so these are the supposed two opposite faces of the crystal. This is one of the opposite face and this is another opposite face of the crystal. Then for these two faces of the crystal, this plane is perpendicular and it contains the direction of optic axis. So such a plane is called as a principal plane. So how many principal planes can be constructed? This type of question can be asked in a MCQ type examination. So how many principal planes can be constructed in case of calcite?
One.
Only one? How many faces are there?
Two. Two. 6 faces.
So what is mean by
6.
if there are 6 faces, so how many principal planes can be constructed? A principal plane is defined as a plane which is perpendicular to the two opposite faces and which contains the direction of optic axis. Hmm?
6.
How 6?
So because it has 6 faces and each face is perpendicular.
We can construct a principal plane which is perpendicular to these two faces. We can construct a principal plane which is perpendicular to these two faces. We can construct a principal plane which is perpendicular to these two faces. So there are 3 principal planes which can be constructed in case of calcite crystal. One principal plane is perpendicular to the face which is BADC and GFEH. ये दो फेसेस को परपेंडिकुलर एक प्लेन हो सकता है. ये एक फेस है for this face and this face we can construct a principal plane perpendicular to these two faces. और ये दो faces को तो मैंने निकाले ही है अभी. For this face and this face we can have a principal plane which is perpendicular. So in total there are 3 principal planes that can be constructed in case of calcite. Option में 3, 4, 6, 2, 1 ऐसे कुछ भी option रह सकते हैं. So in case of calcite there are only 3 principal planes. Is it clear?
Yes, sir.
Okay.
Yes, sir.
Then the principal plane of calcite is a parallelogram having an acute angle of 71 degree and obtuse angle of 109 degree. So with this as a normal, when a beam of unpolarized light is incident with some angle of incidence I, now how I can say that this is unpolarized beam of light? Because here, what is the symbol used over here?
Dots are
Dots and lines, sir.
Dots and lines, they are present simultaneously on each other. So here there is overlapping of lines as well as dots. So dots will represent a vibration which is perpendicular to the principal plane, while this line will show a vibration which is parallel to the principal plane. And here lines and as well as dots, they overlap on each other. So that is why this light is called as unpolarized beam of light. Now when such unpolarized beam of light is incident with some angle of incidence I, then instead of a single refracted ray, here we obtain 2 refracted rays. So this is one of the refracted ray which has vibrations parallel to the principal plane, while the other refracted ray will have vibrations perpendicular to the principal plane. The ray which has vibrations parallel to the principal plane is shown by lines. The ray which has vibrations perpendicular to the principal plane is shown by dots. So here the ray which has vibrations parallel to the principal plane is known as extraordinary ray, while the ray which has vibrations perpendicular to the principal plane shown by dots is known as ordinary ray, or it is simply known as O ray. So here both of these two rays, they are completely plane polarized light. This extraordinary ray is completely plane polarized. It has vibrations in only one plane, while this ordinary ray is also completely plane polarized. It has vibrations also in one particular plane, which is perpendicular to the plane of the principal plane of the calcite. Is it so?
Yes, sir.
Okay. Now, this is the phenomena of double refraction. Here we obtain two refracted rays. That is why it is called as the phenomena of double refraction. And if we can eliminate one of the refracted ray, can we produce the completely plane polarized light? If I can eliminate,
Yes, sir.
if I can eliminate this ordinary component of light, then what I will have? I will have only the extraordinary ray. How is this extraordinary ray? It is completely plane polarized. If I can eliminate this extraordinary ray, then what will I have? I will have only the ordinary ray, which is completely plane polarized. So I can eliminate either the ordinary ray or extraordinary ray, and I can achieve the plane polarized light by the phenomena of double refraction. And that I can do with the help of a nickel prism, which you might have studied in 12th standard, that in the construction of nickel, that it is cut along, this calcite slab is cut along its shortest diagonal, so that it is divided into two halves, and again again these two halves are pasted together with a layer of a material, a transparent paste of a material called as Canada balsam, such that the refractive index of Canada balsam, it lies between that of the refractive index for ordinary ray and refractive index for extraordinary ray, so that when the when the ordinary ray is allowed to pass through this layer of Canada balsam, then it gets totally internally reflected, and we can eliminate the ordinary component and transmit only the extraordinary ray in order to produce the completely plane polarized light. Do you remember this nickel prism? Hello?
Yes, sir.
Okay. Then out of these two rays, that is ordinary ray and extraordinary ray, it is the ordinary ray which follows the Snell's law of refraction, which is mu is equal to sin I upon sin R, while the extraordinary ray, it does not follow the Snell's law of refraction. What does it mean that ordinary ray follows the Snell's law of refraction and extraordinary ray does not follow the Snell's law of refraction? What is Snell's law of refraction? Mu is equal to sin I upon sin R. So if I say sin I upon sin R, if I say that this ordinary ray follows this Snell's law of refraction, what does it mean?
Sine of angle of incidence upon sine of angle of refraction. If we calculate that, then it will be equal to the refractive index.
No, it is equal to refractive index, that is okay. But if I say that this ordinary ray follows the Snell's law of refraction, it means that if I keep on changing the angle of incidence I, if I keep on changing the angle of incidence I here, the angle of refraction R for the ordinary ray, this angle of refraction R for the ordinary ray, it changes in such a way that every time when I calculate this ratio sin I upon sin R, it remains constant. Are you getting my point?
Yes, sir.
If initially if the angle of incidence I is suppose 30 degree, then angle of refraction R changes to say suppose 32 degree, and if I calculate this value, if it comes out to be say suppose 1.32, then the next time when I make this angle of incidence I to be say 35 degree, then the angle of refraction changes as say suppose 38 degree. So sin 35 by sin 38, again if it comes out, this is just an example, not exact. So if it comes out to be again 1.32, what does it mean? It means that refractive index mu for the ordinary ray, it remains same. Though this is a asymmetric crystal or anisotropic crystal, that is physical properties are different in different direction, but for ordinary ray, the physical properties of the crystal will remain same. That is refractive index comes out to be constant in all the directions. So in this direction or this direction or this direction or this direction, any direction, this ordinary ray it travels in any direction throughout the crystal with the same velocity, or why with the same velocity? Because it faces the same refractive index in all possible directions. Is it clear to everyone?
Yes, sir.
But for the extraordinary ray do not follow this Snell's law of refraction. It means that every time when I change the angle of incidence, the angle of refraction for this extraordinary ray, it changes in such a way, this angle of refraction for the extraordinary ray, it changes in such a way that every time this ratio comes out to be different. So for the first case, if it is suppose 1.32, in the next case if it comes out to be 1.37, then 1.41, and so on. What does it mean? It means that refractive index is changing continuously. If the refractive index changes continuously, means its velocity is also different in different directions. So velocity for extraordinary ray is different in different direction, but velocity for ordinary ray is same in all direction. Further, the physical properties of the crystal remains constant along the direction of optic axis, and therefore even for extraordinary ray, though the velocity for extraordinary ray is different in different direction, but along the direction of optic axis, this extraordinary ray will also travel with the same velocity as that of the ordinary ray. So along the direction of optic axis, velocity for extraordinary ray as well as velocity for ordinary ray, it remains same because their refractive index remains same along the direction of optic axis, because physical properties of the crystal remains same along the direction of optic axis. Is it clear?
Yes, sir.
Yes, sir. Yes, sir.
Then next is Huygen's theory of double refraction. So Huygen gave his wave theory of light, and he also explained the phenomena of double refraction based on the following assumptions: that every point in a double refracting medium is a source of two types of wavefronts. One of the wavefront is the ordinary wavefront, which is spherical, as ordinary waves travel with the same velocity on all directions, and the refractive index of the crystal is same for these waves in all directions. So according to Huygen, when an unpolarized beam of light is incident on the slab of a calcite crystal, which is a double refracting crystal, if it is incident by an unpolarized beam of light, then according to Huygen, two wavefronts should originate, one for the ordinary ray, which is spherical in shape. Why spherical in shape? Because the velocity for ordinary ray is same in all the directions, while the wavefront which is traced for the extraordinary ray is elliptical in shape, and the velocity for, if this is the direction of suppose optic axis, then the elliptical wavefront, it lies outside the spherical wavefront, but both the wavefronts, they will touch each other along the direction of optic axis because their velocities are same along the direction of optic axis. So for extraordinary wavefront, so one of the wavefront is ordinary wavefront, which is spherical, as ordinary waves travel with the same velocity in all directions. The refractive index of the crystal is same for these waves in all directions, while extraordinary wavefront, which is ellipsoidal, as these waves travel with different velocity in different directions, so the refractive index of the crystal for these waves is different in different directions. Is it clear?
Yes, sir.
Yes, sir.
Okay. Now the ordinary waves and extraordinary waves travel with the same velocity along the optic axis, which I already mentioned you. Hence the two wavefronts, they will meet at the optic axis. Now in some crystals, the velocity VO, this O suffix indicates that it is the velocity for ordinary waves. So in some crystals, the velocity VO of the ordinary waves is greater than the velocity VE of the extraordinary waves in all directions except along the optic axis. So such crystals, they are known as positive crystals. So there are two types of crystals. One is called as a positive crystal, another one is known as a negative crystal. Now look at here. Here this is the direction of optic axis. So this is the direction of optic axis, that is direction along which physical properties of the crystal remains constant, and according to Huygen's theory, two wavefronts will originate, one for the ordinary wave which is spherical in shape, because velocity for ordinary wave is same in all directions, while the wavefront which is traced for the extraordinary wave is elliptical in shape, because the velocity for extraordinary wave is different in different direction. And now look at here, the elliptical wavefront and the spherical wavefront, both of them, they touch each other along the direction of optic axis. Here the elliptical wavefront and the spherical wavefront, they touch each other along the direction of optic axis, because of the fact that the velocity for extraordinary wave as well as ordinary wave is same along the direction of optic axis, because the refractive index for extraordinary wave as well as ordinary wave, it remains same along the direction of optic axis, because physical properties of the crystal remain same along the direction of optic axis. But look at the direction which is perpendicular to the direction of optic axis. So this is the direction which is perpendicular to the direction of optic axis, and what do you observe over here? What do you observe in a direction which is perpendicular to the direction of optic axis?
Both the wavefronts do not touch each other.
Do not touch each other means which wavefront is lying outside here?
O wavefront is outside.
O wavefront is outside means the spherical wavefront is lying outside the elliptical wavefront, means the velocity of which wavefront is more?
Ordinary wavefront.
O wavefront.
Here the velocity for ordinary wavefront is more as compared to the velocity of the extraordinary wavefront. So here VO is greater than VE. If VO is greater than VE, it means that obviously the refractive index for ordinary ray is less as compared to the refractive index for extraordinary ray in this direction. Refractive index is something which is resistance to the velocity of light in a medium. So if velocity is more, it means that refractive index is less. If velocity is less, it means that refractive index is more. So here the velocity VE, velocity of the ordinary ray, here as the elliptical wavefront lies inside the spherical wavefront, it means that velocity of extraordinary ray is less as compared to the velocity of ordinary ray, isn't it?
Yes, sir.
So it means that if velocity is less, it means that refractive index for extraordinary ray is more as compared to the refractive index for ordinary ray. So here mu E is greater than mu O, isn't it?
Yes, sir.
So such crystals in which VE is less than VO or mu E is greater than mu O, such crystals in which the elliptical wavefront lies inside the spherical wavefront, they are called as positive crystals. Such crystals are called as positive crystals, and the example is quartz and ice. So example of positive crystal is quartz and ice. While in some crystals like calcite, here now see, this is the direction of optic axis, and the wavefront which is traced by ordinary ray is spherical in shape, while the wavefront which is traced by the extraordinary ray is elliptical in shape. And you can see that here the elliptical wavefront is now lying outside the spherical wavefront, but both the wavefronts, they touch each other along the direction of optic axis. So here along the direction of optic axis, both of them, they are touching each other. But look at the direction perpendicular to the direction of optic axis. So what do you observe here?
Velocity of extraordinary wavefront is more than the ordinary wavefront.
Velocity VE, velocity for extraordinary ray is more as compared to the velocity for ordinary ray. Here the spherical wavefront lies inside the elliptical wavefront. It means that here the ordinary wavefront, it lags behind the extraordinary ray in this direction. So here velocity for extraordinary ray is more as compared to the velocity for ordinary ray. It means that refractive index for extraordinary ray mu e is less as compared to the refractive index for ordinary ray, which is mu o. So certain crystals in which VE is greater than VO or mu E is less than mu O, such crystals are termed as negative crystals, and calcite and tourmaline, these are the examples of negative crystal. Is it clear?
Yes, sir.
So there are two types of double refracting crystal. One is called as a positive crystal, other one is called as negative crystal. The difference between the positive and negative crystal which I have taken over here, this is very important from MCQ type examination. You might be given a statement like, if the elliptical wavefront lies inside the spherical wavefront, identify the type of a crystal. ऑप्शन में दिया रह सकता है anisotropy crystal, isotropic crystal, positive crystal, negative crystal, something like that. So if the elliptical wavefront lies inside the spherical wavefront, then it is a positive crystal. While if the elliptical wavefront is lying outside the spherical wavefront, then it is called as a negative crystal. या फिर ऐसा भी क्वेश्चन हो सकता है that quartz is an example of, and ऑप्शन में हो सकते like positive crystal, negative crystal, anisotropic crystal, isotropic crystal, like that, symmetric crystal, ऐसा कुछ भी ऑप्शन बना के पूछ सकते हैं. So quartz is an example of a positive crystal. Is it clear?
Yes, sir.
Or
Yes,
it
sir.
can be asked in the form of this relation, that if VO is greater than VE, identify the type of crystal. If VO is greater than VE, identify the type of a crystal. Or if mu E is greater than mu O, identify the type of crystal. Like that. So number of questions can be framed on this topic, and therefore this is very important from exam point of view. Please note down this, the difference between positive and negative crystal. So is it clear
Yes, sir.
how the phenomena of double refraction takes place?
Yes.
Okay.
Yes, sir.
Then next important topic is propagation of light in double refracting crystals such as calcite. So we study the propagation of light in double refracting crystal such as calcite, which is a negative crystal which we have right now seen, and it has been studied under three different cases. Case 1 is when optic axis is perpendicular to the crystal surface. Case 2 is when optic axis is parallel to the crystal surface, and case 3 is when optic axis is inclined to the crystal surface. So let us discuss these cases one by one. Let us discuss case 1, that is when optic axis is perpendicular to crystal surface. So this, let us cut the slab of a calcite crystal in such a way that optic axis is now perpendicular to the crystal surface. So this is the crystal surface, and here the direction of optic axis is perpendicular to that of the crystal surface. Now when a beam of unpolarized light is incident, so again it is unpolarized, so it is shown by lines as well as dots, both are present simultaneously on it. So when an unpolarized beam of light is incident on the slab of calcite crystal such that optic axis is perpendicular to the crystal surface, then calcite being a double refracting crystal, two wavefronts will originate according to Huygen's wave theory of light. One of the wavefront is spherical in shape, which is for the ordinary ray, while the other wavefront will originate for the extraordinary ray, which is elliptical in shape, and both these wavefronts, they will touch each other along the direction of optic axis. So if both the wavefronts, they touch each other along the direction of optic axis, and if I am an observer over here and I am observing the light which is coming towards me, can I make the distinction between the two components?
No, sir.
The extraordinary ray is shown by lines because the extraordinary ray has vibrations parallel to the principal plane of the calcite crystal, while ordinary ray is shown by dots, which shows that the vibrations are perpendicular to the principal plane of the calcite slab. So being an observer over here, can I make the distinction between the two?
No, sir.
No. Why? Why I cannot make the distinction between the two rays?
Because they are closer to each other.
Closer nahi. They are overlapping on each other.
Overlap.
Here
Yes.
the wavefronts for ordinary ray and extraordinary ray, they touch each other along the direction of optic axis at every point. So here the velocity for ordinary ray is exactly same as that of the velocity for extraordinary ray. So if both the rays are traveling in the same direction with the same velocity, can you make the distinction between the two rays? No. And therefore this case 1, that is when optic axis is perpendicular to the crystal surface, is of no use for us, because we cannot make the distinction between the ordinary ray and extraordinary ray, as there is overlapping of the two rays due to the fact that they travel in the same direction with the same velocity. Then let us discuss case 2, that is when optic axis is parallel to the crystal surface. So now let us say that this is the direction of optic axis, so that it is now parallel to that of the crystal surface. So this is the crystal surface and this is also the direction of optic axis. So we cut the slab of calcite crystal in such a way that optic axis is now parallel to the crystal surface. Again, let a beam of unpolarized light is incident on this calcite slab. So calcite being a double refracting crystal, two wavefronts will originate, one for the ordinary ray which is spherical in shape, another wavefront will be elliptical. Calcite is a negative crystal, so the elliptical wavefront will lie outside the spherical wavefront, but both the wavefronts, they will touch each other along the direction of optic axis. So this is the direction of optic axis, and both these wavefronts, they will touch each other on the direction of optic axis. But what will happen in a direction which is perpendicular to that of the direction of optic axis? So now here this is the direction which is perpendicular to the direction of optic axis. What happens in the direction perpendicular to that of the optic axis? You are just observing this case, like here. This is the slab of calcite crystal. So this is the direction of optic axis and this is the crystal surface. And this is the direction which is perpendicular to that of the direction of optic axis. What do you observe in this case?
Yes, sir.
What is, sir? What do you observe in this direction?
VE is greater than
VE is greater than VO. So here
VO.
elliptical wavefront lies outside the spherical wavefront. It means that the extraordinary ray, it travels faster as compared to that of the ordinary ray. Here velocity for extraordinary ray, VE, is greater than the velocity for ordinary ray. VE is greater than velocity for ordinary ray. So here the ordinary ray, it will lags behind the extraordinary ray, and the ordinary ray and extraordinary ray, they travel in the same direction but with different velocities, and therefore we can make the clear distinction between the ordinary ray and extraordinary ray, as well as this case can be used to introduce a desired optical path difference between the two, because one of the ray, here ordinary ray, is retarded as compared to that of the extraordinary ray. It lags behind the extraordinary ray, and therefore we can introduce a desired optical path difference between the ordinary ray and extraordinary ray. So as we can introduce a desired optical path difference between ordinary ray and extraordinary ray, and therefore this case 2 is useful for us in order to construct the retardation plates. The name itself, that is retardation, it suggests that it is used to retard one of the ray from the other. So retardation plates are of two types, further of two types. One is known as a half wave plate and other one is known as a quarter wave plate. So half wave plate and quarter wave plate, these are the two types of retardation plates. This half wave plate means if we select the thickness of this plate in such a way that it introduces a desired optical path difference of lambda by 2 between the ordinary and extraordinary ray, then such wave plate is known as half wave plate. While if we can choose the thickness of this plate in such a way that we can introduce a desired optical path difference between ordinary ray and extraordinary ray such that it is equal to lambda by 4, then it is called as a quarter wave plate. Is it clear?
Yes, sir.
So such case 2 is used in construction of retardation plates, with the help of which we can introduce a desired optical path difference between the ordinary ray and extraordinary ray, because they are traveling in the same direction with different velocities. So we can make a clear distinction between the two, and we can also introduce a desired path difference. Let us discuss this case 3. So when optic axis is inclined to the crystal surface, so now this is the crystal surface and optic axis is inclined with respect to that of the crystal surface. So again, when a beam of unpolarized light is introduced, then two wavefronts will originate, one for the ordinary ray and which is spherical in shape, and this wavefront will travel along this direction, while we have seen just now that the velocity for extraordinary ray is maximum in which direction? For calcite crystal, velocity for extraordinary ray is maximum in which direction?
Along the optic axis.
Along optic axis.
All directions. All directions.
I am asking for velocity for extraordinary ray is maximum in which direction?
Perpendicular to optic.
It is maximum in a direction which is perpendicular to the direction of optic axis. This velocity is maximum. So
Yes, sir.
so here the ordinary ray will travel along this direction, because the wavefront is spherical. It means that it has the same velocity in all possible direction, but the extraordinary ray will travel in a direction which is perpendicular to the direction of optic axis, because its velocity is maximum in this direction. So as this is the direction of optic axis, so this is the direction which is perpendicular to the direction of optic axis. Here the angle is 90 degree. So in this direction, which is perpendicular to the direction of optic axis, since the velocity for extraordinary ray is more, so extraordinary ray which has vibration parallel to the principal plane shown by lines, it will travel along this direction, while the ordinary ray which has vibrations perpendicular to the principal plane shown by dots, it will travel along this direction. So can we make a clear distinction between the ordinary ray and extraordinary ray with the case 3?
Yes, sir.
Yes, we can make the clear distinction between ordinary ray and extraordinary ray. But can we introduce a desired optical path difference?
No, sir.
No. Why? The reason is they are traveling in different direction with different velocities, and therefore this case cannot be used to construct the retardation plate. Here we can just use this case to separate the ordinary ray and extraordinary ray. They will travel in different direction with different velocities, but we cannot use it to construct the retardation plate. While here only this case 2 is important for us, because we can make the clear distinction between the ordinary ray and extraordinary ray, as well as this case can be used to introduce a desired optical path difference between the two rays, and therefore it is useful for construction of retardation plates also. So this case 2 is important, while this case 1 is not useful, as we cannot make the distinction between the two, since both the rays they travel in the same direction with the same velocity. Here we can identify or distinguish between the two rays, but we cannot use it to have the we cannot use it to produce the retardation plate, because the two rays they travel in different direction with different velocities. Is it clear? The three cases, that is propagation of light in double refracting crystal.
Yes, sir. Yes, sir.
Now instead of a calcite crystal which we have discussed, which is a negative crystal, if it would have been a quartz crystal which is a positive crystal, what changes should be there for quartz which is a positive crystal?
So the ordinary axis will be outside and the extraordinary axis will be inside.
It's not axis, it is the wavefront.
Wavefront, sorry.
So in this case the ordinary wavefront will be spherical in shape, and it will lie outside the elliptical wavefront. So here the elliptical wavefront will lie inside the spherical wavefront, because the velocity for extraordinary ray will be less as compared to the velocity for ordinary ray. Is it clear to you?
Yes, sir.
So for positive crystals such as quartz, here the the extraordinary ray will lag behind the ordinary ray, while for the calcite crystal, which is a negative crystal, it is the ordinary ray which will lag behind the extraordinary ray. Then next is polarides. You might have encountered with this word, which is Polaroid, and it is now a very common word. That is, when you go for shopping, you search for the Polaroid sunglasses, isn't it? They are also costlier.
Yes, sir.
Yeah.
Yes, sir.
These Polaroid sunglasses are used to avoid the glare of light, and it gives a very good quality image of the object. Similarly, there are Polaroid sheets which are used in the windshield of a car, and such Polaroid sunglasses or Polaroid windshields of car, they are used to protect us. They are used to protect our eye from the extra glare of light. If you are driving in night, and if any vehicle comes from the opposite side, and if it has a very strong headlights, then it causes glare to your eye, and due to that it may lead to the accidents. So in order to avoid that glare of light, we use the Polaroid sunglasses, or we use the Polaroid windshields of the car. So whenever light is reflected from any transparent surface, it is polarized in one particular fashion, and that polarized wave, it causes the glare, and due to that glare the image is not clear. So here you can see the difference between the windshield of a car. Here this car is not coated with any Polaroid sheet, while here the car is coated with a Polaroid sheet. Now, due to excess amount of glare of light which is falling on this glass plate, which is the windshield of the car, here you cannot see the steering of the car clearly. But here the light which is incident, it is unpolarized beam of light, and when it passes through the Polaroid windshield, the amount of intensity of light which passes through it is less, and then here you can clearly see or identify what is there inside. So you can clearly mark the distinction between the Polaroid windshield and unpolarized windshield of the car. Here also this slide shows that this window is having no film, which is a Polaroid film, while here this window is coated with a Polaroid film. So here you can see that there is absence of this chip due to excessive glare of sunlight, while here you can clearly identify that there is a position of chip. So you get a good quality image. See this animation. Here the light which is coming from sun, it is polarized in all direction, and therefore it is called as unpolarized light, because here the electric field vector, it vibrates in all possible direction. So when this light is reflected from the surface of road, and when it enters through the Polaroid sun glass, then it will absorb some of the vibration, and it will transmit only that vibration to pass through it, which has its polarizing directions parallel to its axis, and therefore here we get the plain polarized light. So this light is having less intensity as compared to the intensity of light over here. Here this light is highly intense, because here the electric field vector is vibrating in all possible directions. Here the electric field vector is vibrating in all possible directions. So here the intensity is added up, while when such light is transmitted through the Polaroid sunglasses, it will absorb all other vibrations except those vibrations which are parallel to its axis, and such vibrations are transmitted through it. So here the intensity is less as compared to this intensity. Then it will avoid the glare of light, and here hence we can see a good image. Is it clear about what is meant by Polaroid sunglasses?
Yes, sir.
Okay. Then the next application of polarization is LCD, that is liquid crystal displays, and these liquid crystal displays are used in your calculators, or watches, digital watches. You know that each digit is fabricated with the help of these 7 segments, such as A, B, C, D, E, F and G, and these 7 segments, when they glow, they produce a digit. So when you press a 0 on your calculator, or if you press a 2 on your calculator, immediately these segments, they will appear as dark, like C, D, A, E, F. These segments, they will appear as dark or black, and therefore the digit 2 is displayed on your calculator, or it may be your digital watch. So how this 7 segmental display is constructed with the help of phenomena called as polarization of light is, you have studied about optically active substances in chemistry in 12th standard, and there are 2 types of optically active substances, that is dextrorotatory and levorotatory. So optically active substance means the substance which has the ability to rotate the plane of incident vibration when a plane polarized light is incident onto it. If the optically active substance rotate the plane of incident vibration towards right hand side or in clockwise sense with respect to the observer, then it is called as dextrorotatory substances. And if the optically active substance can rotate the plane of incident vibration towards his left hand or in anti-clockwise sense, then it is called as a levorotatory substances. So here look at the construction. Here, in order to understand, you can take here any tourmaline crystal or nickel prism, anything, as polarizer and analyzer. For the sake of simplicity, I have taken here the slits. So the first slit is called as a polarizer because it is used to produce the plane polarized light, while the second slit is called as analyzer. Now you can see the polarizing directions of these 2 slits. Here the polarizing directions of these 2 slits are such that they are perpendicular to each other, or you may say that the polarizer and analyzer are oriented in such a way that their polarizing directions are perpendicular to each other. Is it clear?
Yes, sir.
Okay. Then in between the polarizer and analyzer, an optically active substance is kept, and behind the analyzer there is a position of a mirror. So when an unpolarized beam of light is incident on the polarizer, what is the function of this polarizer is, it will allow only that vibration to pass through it which is parallel to its axis. So only this vibration which is parallel to the axis of this polarizer will be transmitted through it. Now when this vibration is incident on the optically active substance, this optically active substance is selected in such a way that it will rotate the plane of incident vibration by exactly 90 degrees. So when this plane polarized light passes through this optically active substance, then this optically active substance rotates the plane of incident vibration by 90 degree completely. So when this vibration is rotated by 90 degree, now is this vibration parallel to the axis of the second analyzer?
Yes, sir.
So this vibration becomes parallel to the analyzer, and therefore such vibration is transmitted through the analyzer and it is incident on the mirror. So again when it gets reflected back from the mirror, then this vibration will be transmitted through the analyzer again, and it is incident on the optically active substance. Again this optically active substance will rotate the plane of incident vibration by 90 degree, and again this vibration will be transmitted through the polarizer. And if I am an observer over here, I will observe this light to be of maximum intensity. So I will observe here the brightness. So being an observer over here, I will observe this position to be bright. While when you apply some potential difference to this optically active substance, then this optically active substance immediately loses the phenomena of optical rotation. Now if I perform the same experiment again, then when an unpolarized light is allowed to fall on the polarizer, here you get a completely plane polarized light, because that is the function of polarizer. But when as soon as I apply a voltage to this optically active substance, this optically active substance loses the phenomena of optical rotation, and therefore these vibrations will remain as it is. So these vibrations are not at all rotated by any angle theta. So now, are these vibrations parallel to the axis of analyzer?
No, sir.
No. So these vibrations, since they are not parallel to the axis of analyzer, so they are not transmitted through the analyzer, and hence no vibration will be incident on the mirror, so there is no reflection back from the mirror, and therefore if an observer is observing this position over here, this observer will observe as darkness. So this position will appear as dark, and this is what happens in case of a 7-segmental display. Here each segment, that is A, B, C, D, E, F and G, each segment, it consists of an optically active substance which is kept between the polarizer and analyzer, and behind that there is the position of a mirror. So when you press 2 on the calculator takes the signal that voltage has to be applied to the segments which are C, D, A, E and F, while no voltage should be applied to the segments which are B and G. So the segments B and G, they appear as bright or white, while the segments like C, D, A, E and F, as soon as you apply voltage to these segments, they loses the phenomena of optical rotation, and due to that this observer observes these segments over here as dark. So that is why here the digit 2 is displayed on your screen, while the segments, that is B and G, for these two segments no voltage has to be applied, so they will rotate the incident vibration, and here they will observe the brightness. Is it clear?
Yes, sir.
So this is the construction which is shown over here in this slide again, that each segment, it consists of an optically active substance. So when you apply the voltage to the segments such as this one, in order to give the digit 5 on the screen, so you need to apply voltage to these segments, that is this segment, then this segment, then this segment and this segment. So when you apply voltage to these segments, it will take the signal that no voltage has to be applied to the segment this one and this one. So these two segments, they will appear as bright. So these two segments, they will appear as bright, while the rest of the segments, they will appear as dark. So this is how you get the digital display.
Yes, sir.
Okay. So here we finish with the polarization of light.